So to put this in intuitive perspective, let's suppose that you want to know the probability that you are sick. Probability that I am sick is what? What's the probability that your daughter's sick? Interestingly, I didn't actually write the expression correctly here, because right now I said given nothing. And notice that if there's no given, that means pretend we don't know anything. So I don't know that your daughter might have it right now. I don't know that her nose is runny. What this actually says is, what's the probability that she's sick? Given nothing, just the standard assumptions that we live on planet Earth and things like that. And the odds are, whatever the probabilities are, that somebody is sick, which is probably 1 out of some big number, right? It's probably not that big, because people are sick at least once a year. We'll say 1 out of 1,000, right? Okay. What's the probability that your daughter is sick given that she has a runny nose? Probably a lot higher, right? Okay. Suppose we wanted an exact number. That's kind of hard to measure, isn't it? But we can measure the probability that you have a runny nose given that you're sick. Because doctors collect stats like that, right? 10,000 people have come. We know this many of them are sick because the doctor says so, and doctors are never wrong. And of those, some percentage of them actually have runny noses. So suppose doctors actually put a number on this and they say 1 out of 10, well, I'll say 2 out of 10 people who are sick have runny noses. And this is being kind of silly now. Okay, well then, what is the probability of being sick in general? We already told you it's 1 out of 1,000, right? Okay. Finally, the last thing we need is a normalization constant. And we're going to say, what's the probability of having a runny nose? And this is the one that throws people off, because it's hard to forget that we are doing this given that we're conditioning it upon another concept. But we actually need to ask ourselves, what's the probability of runny nose without that constraint? And that's actually going to be a different probability. Another way to get some intuition for this term of Bayes' law is, this is a normalization term. It's only there to make the probability correct. It'll be proportional whether or not you use this term at all. But if we can determine the probability of runny nose from the population at large, then we can finally solve this problem.
0.3.
Okay, 0.3. Well, oops, I typed 43. 0.3. Great, we have these 3 terms. We plug them into this equation. We compute that, and now we know the probability that you're sick given a runny nose. And because, I guess here's the main thing. When people come up with equalities in the world, they're always based on some assumptions. This is one of the very few equalities in the universe that have ever been derived that has no assumptions. This equality is true assuming nothing. Like, that's just how probabilities work. And that's kind of one of the reasons why Bayes' law is such a big deal, is it's applicable with no major assumptions. I mean, I guess we're assuming math is true, and we're assuming, consistency in the universe and a few other things that we had to do to even produce this basic example. So we're assuming 1 + 1 is 2 and things like that. But there's not really any assumption that we're in a specific domain. There's not any assumption that these probabilities themselves are sufficiently well defined that it's not, you don't really have to qualify what you mean usually. And so this makes probabilities very attractive, is the basics of what I'm getting at. Okay. All right, well, let's just move on. One other bit of groundwork is, where am I? I am lost. Back to the table of constants. Belief networks. Okay, if you took my AI class, I can't remember, how many of you guys did take my AI class? 1, 2, 3, okay, some of you, not all of you. I really hammered in the concept of utility theory. Do you remember that? Okay, and I did that for a reason, is if you know this and you know that and you have these probabilities of this outcome happening, you can build this big tree and then you can calculate what decisions are optimal under various conditions. And if you didn't take that class, you're welcome to go back and reread this chapter if you want to. This is the one just before the belief networks chapter that we're going to be working on for our next assignment. So it's some good background for you, but I don't think there's anything in it that's absolutely essential for doing it. It just gives a lot of context for it. So if you have a little extra time, go read the chapter just before it, and it'll give you an idea of some of the background that my AI class gives you for utility theory. And here we come to probabilistic graphical models, also known as belief networks or Bayes nets or Bayesian belief networks and things like that. Let us consider, here's an arbitrary belief network. And this, by the way, this is not the true model of planet Earth the way it really works. This is my, what's it called? Subjective diagram of how some things kind of seem to work at the moment I was writing this. And I don't necessarily still agree with this. But in belief networks, we draw arrows to imply causality. So I'm suggesting here that whether or not you are intelligent is partly a factor of whether you got lucky and have some genes from really intelligent parents, and it's partly a factor of whether or not you worked really hard to learn, right? And I'm also suggesting that whether or not you get a good SAT score has something to do with your intelligence, but it also has something to do with, did you fill in the right bubbles, and did you get an easy question that year, and things like that. I'm suggesting that whether or not you get into a university has a lot to do with your SAT scores. And I'm suggesting that whether you know how to get a good career has a lot to do with whether or not you got into a university, but also whether or not you're intelligent, and also whether you're persistent. And if you have all those three things, persistence, intelligence, and a good university degree, chances are pretty darn good you've got a good career. And I'm suggesting that if you have a big degree and a nice career, you probably have some wealth. Can you see that there's some reasonably good causality connections here? Okay. So if we were trying to predict how wealthy you are, we might start with these things and infer other things, and then we could eventually assign some probability distribution to how wealthy you are. Do you agree? Okay. What's neat about Bayes networks, or graphical models, whatever we want to call them, is while yes, the arrows are all directional, and for reasons I don't understand, they like to go down in Bayes nets. So I'm trying to follow the convention here by always pointing downward. That seems kind of pessimistic, doesn't it? Oh well, whatever. They like to go downward unless they're doing over time, then they usually go to the right for whatever reason. So although the causality tends to flow downward, the inference can go any direction we want. Well, this is going to tie back to, do you remember we talked about relaxation networks? Essentially, it's a relaxation network. So suppose I want to say, hey, we know this person is wealthy. We could clamp a value of wealth on this person and say, hey, your wealth is this number. And we also know that you went to a university, and so we can clamp another value here. And we can observe whatever we want to observe about this network. And then we're going to let the other things relax, the things we don't know, like whether or not you had career options and whether you were persistent. And then we'll do a bunch of math to let the thing relax. And when we're all done, we'll be able to assign a number to how lucky you are and how much persistence you have. And then if this graphical model truly represents the universe, then the numbers that we infer for the various nodes in it, we can say are actually correctly inferred representations of those values. That's kind of the whole idea behind graphical models. Does that make sense? Okay. Cool things about them are, we're not just assigning numbers to all the units, we're assigning distributions to all the units. So not only is it going to approximate the truth, it's going to approximate the truth with approximately truthful distributions. assuming your graph is approximately truthful, which it never is. But the point is, this allows us to do any kind of inference and reasoning, in theory, that you can represent with a causal graph. And that's kind of impressive in my opinion, because I think you can see there's some degree of interestingness to this. You can measure some of these things, you can't measure some of the others, but wouldn't it be cool to assign distributions to those and see if you can then label people and put them into buckets? Or whatever you want to do, okay? Yeah, sometimes I feel bad how hard I'm working to enable prejudice and discrimination, but that's not really what we're trying to accomplish here.
We have to know what labels on the buckets.
Yeah. Okay, so let's go back to the mushroom problem. Suppose you had, this is 98% probability that this is actually a death cap, and then you had over here, how much I value my life. And you could actually find out that based on all of that, there's some probability that you will actually eat the mushroom, right? Or is there a probability you'll eat the mushroom? Well, that implies how much you actually value your life. Can you actually put a quantity on the value of life? Well, you can if you use this technique. Of course, people will tell you you've done it wrong because there's no way that did it right, but no one can find any mathematical flaws in it anyway. So if the graph is correct, you can put a value on the quality of life. Okay, kind of the difference, one difference between utility theory that we taught in AI class and belief networks is now we're no longer making the assumption that there's a single value to any node. We're now putting distributions on every node. And we're no longer making the assumption that it's directed and acyclic. Now we can build any graph in the world that you want, and we'll be able to compute exact distributions for it, and that's kind of neat. So, and by exact, I mean we'll be able to sample from the distribution until you're satisfied that it's exact enough. There is something called exact inference, which I'm not going to cover because it's math that's way over my head, but we're going to do the computer approximation version of it because in my opinion that's good enough. All right.